Today, our speaker is Enrique Delgado from University of Sevilla, and he will talk about a posteriori error estimates for greedy algorithm in reduced basis method. The floor is yours, Enrique. Thank you.
Thank you, Virgul. Thank you all for coming here to share these seminars. I'm going to talk about some posteriori error estimators that we use in the greedy algorithm in order to construct reduced basis methods. Wait. Okay. The talk is divided in two parts. First part, I will introduce you a classical, let's say, posteriori error estimator based on the Bresira-Patravia theory for LPS, VMS, Smagorinsky turbulence model. And then in the second part of the talk, I will present you a novel a posteriori error estimator that is based not in mathematical theory, but on the physics properties of the solution. We apply this Kolmogorov posteriori error estimator into an steady Smagorinsky model. Okay. The first work I'm going to talk is a work in collaboration with Tomás Chacón and Macarena Gómez. As I said, it's a Bresira-Patravia a posteriori error estimator, the classical one, but applied to an LPS, local projection stabilization, VMS Smagorinsky model. I'm going to recall you what is the Smagorinsky model means. This basically, the Smagorinsky model consists on the Navier-Stokes equation, okay, where we are adding an eddy viscosity term in order to modelize the turbulence. This eddy viscosity term is a high nonlinear term that is given by this quantity. These are some constant. Hk is the length of the element, and although this is a fully discrete model, I'm presenting you in a continuous form in order to compare it with the Navier-Stokes equation. As a parameter for the reduced basis method, we are considering the Reynolds number, okay? And we will see it later on. We have to deal with this nonlinear term in order to construct in an efficient way the reduced basis model. So, as I said to you before, we are not considering this classical Smagorinsky model because it's over-diffusive. So we consider an enhanced method that is a variational multi-scale Smagorinsky model in which we are decoupling both the pressure and the velocity space. We decouple the velocity and pressure space in a direct sum of the resolved scales, large resolved scales, and the small resolved scales. We are solving both large and small scales for both pressure and velocity. Just applying an interpolator over the finite element solution. Okay. The Smagorinsky term that we are considering is not longer the classical one, but we are considering this filtered Smagorinsky term for the grading of velocity and the grading of in the variational formulation for the velocity gradient. Okay. Moreover, we are considering for pressure a pressure stabilization term in order to avoid use the classical P2, P1 and obtain better accuracy on the pressure solution. So we are considering this filtering also for the filtering term also for the pressure, and this stabilization term that is given by this nonlinear quantity. Here mu, I forgot to change it. This mu corresponds to the Reynolds number. okay? And this UK is a fixed velocity on each element. And this new T bar is a fixed viscosity term, okay? This stabilization coefficient depends both on the solution, the velocity, and on the parameters. So later on, I will explain how we have to deal it in the reduced basis framework. This is the VMS Smagorinsky model we are considering. This is the diffusive term, the divergence pressure term. Okay, this B is the divergence operator. This is the convective operator, and this is the Smagorinsky closure. Also, we are considering here in the continuity equation the stabilization term on the pressure. In order to define the reduced basis matrices, we are going to rewrite this variational formulation by this way. We want to make and affine the composition with respect to the parameter in order to store the offline matrices in the reduced basis framework. So we are considering here the diffusive term, okay, the divergence term given by this quantity. Here mu corresponds to the Reynolds number, that is in our case the parameter. We are considering also the convective term, that is a trilinear term. So in some sense, we are not to deal it with non-linearity, since our numerical scheme in the reduced order framework is also a semi-implicit scheme. So by this way, we are not have to deal with hyper-reduction techniques for the convective term. And finally, we have the Smagorinsky term and the pressure stabilization term that, as I'm here highlighting, these both terms are nonlinear function with respect to the parameter. In fact, this is a nonlinear function with respect to the velocity. But in any case, there are nonlinearities that we have to deal with them when we are going to solve it on the reduced basis framework. So what is the reduced basis model that we are considering? We are constructing our reduced basis spaces by means of the greedy algorithm. So for that, in a first stage, we select a parameter value, okay, a random parameter value in the parameter set, and we compute the snapshot for velocity and pressure. Those snapshots will be the velocity and pressure spaces respectively. When we have the a velocity and pressure space of dimension n, how we construct the next space by selecting a new parameter value on the greedy algorithm. So we have to compute the reduced basis solution, okay, by performing a Galedkin projection over the reduced basis space of dimension n, and we will choose the next parameter value as the maximum of the exact error between the high fidelity solution and the reduced basis solution. Of course, this error for each parameter value, even in a discrete set of the parameter setting, is very costly, because we should compute a high number of high fidelity solution. We have to substitute it by an a posteriori error estimator. So from now, we are not selecting the parameter value as the maximum error, but as the maximum of the a posteriori error estimator. Thank you to that, when we have chosen the parameter value, we compute the snapshot for the velocity and pressure. We construct the new parameter, the new pressure space, just adding the pressure snapshot, and for the velocity space, in this case, when we consider the stabilization on the pressure, we have two different strategies. We can compute the classical, for example, the classical supremizer, inner pressure supremizer for the velocity space, and we consider that the velocity space has the velocity snapshots and the inner pressure supremizer, or thanks to having this stabilization term, we can assure also at the reduced order level that the insuf stability constant is fulfilled by means only just adding the velocity space. So when we consider the velocity, the pressure stabilization term also at the reduced order level, we can assure that the insuf stability is satisfied only just having the velocity snapshot for the velocity space. So those two strategies we will compare in the following in order to see what is the best approximation for the velocity space. But let me recall you how we solve the reduced order problem just performing the Galerkin projection over the reduced basis space. Okay, we have to solve it. That, as I showed you before, it should be solving this problem. Okay, we are solving in a fixed point scheme, let's say, for the convective term. So this is trilinear, is not a problem. But here we have these two terms that are nonlinear. So we need to deal with hyperreduction techniques in order to perform efficiently the reduced basis matrices, in order to compute efficiently the reduced basis matrix for solving the linear system. And we deal with the empirical interpolation method. So just considering the empirical interpolation method, we can approximate in some way the two nonlinear terms by means of some functions that depends only on the space, of course, depending on these of some snapshots of these functions, and multiplied by some constants that depends only on the parameter. This sigma j's nu and sigma j's tau only depends on the parameter. So thanks to that, we can decouple those integrals. So at this point, we can store offline perfectly those matrices. It's not a matrix, it's a tensor of 3 elements, okay, but it's not a problem, it's just like the convective term. And also with the pressure stabilization term. So in this way, we have the problem perfectly, the reduced order problem perfectly defined, and we have only to solve in each iteration of the fixed point scheme two linear system in order to obtain these quantities that depends only on mu. Thanks to that, we can solve efficiently this VMS LPS Smagorinsky problem. But what is the a posteriori error estimator? We, as I said you before, we deal with the Brazil-Rapaz-Rabial theory. For that, we need to introduce a velocity norm that is adapted to the problem. This velocity norm is a weight norm of the classical H1 semi-norm, and we use it in order to get better approximation of the constants that appear in the posteriori error estimator. We have to define the Frechet derivative of the operator A, okay, and we have to prove that this operator, this Frechet derivative, is continuous and also insuf-stable. Okay, this means that the operator is well posed. Also, we need to prove that the Frechet derivative is locally Lipschitz with respect to the first variable. Okay, once we have proved this property, we can obtain the a posteriori error estimator for this problem. We need to define the residual because this a posteriori error estimator is based on the residual of the reduced basis solution. So we define this epsilon n as the dual norm of the residual, and also we define this tau n as this quantity, where here beta n is the insuf stability of the Frechet derivative, and this rho t is the constant, is the Lipschitz constant. Okay. Thanks to that, we can define, given by this theorem, that the a posteriori error estimator is given by this quantity. Okay. Of course, this a posteriori error estimator only exists only if this tau n is lower than 1. Of course, if not, it's not defined. If we have this tau value greater than 1 that occurs basically at the first steps of the greedy algorithm, because the residual is not small enough, we can consider, for example, this linearization of the a posteriori error estimator. This is just performing the Taylor expansion of this quantity with respect to mu, and we get the first term of the Taylor expansion. So this a posteriori error estimator is a linearization of this a posteriori error estimator. Of course, we can, for example, take another strategy that is takes the proper tau as an a posteriori error estimator, but the difference is just this tau behaves more or less like the a posteriori error estimator. That depends, because it depends on basically on the residual, but is in some sense lived with respect to the posteriori error estimator. So by this way, we obtain a smoother, let's say, a posteriori error estimator. But in any case, we can choose both in any case, and the results are practically the same. We will see in the following. So we can prove that if, of course, the Frechet derivative, if insuf-stable, and this value tau is lower than 1, then there exists a unique solution of the finite elements of the high fidelity problem, that the error, the exact error, is below of the a posteriori error estimator. We are certifying that the error is below of our a posteriori error estimator. So in the greedy algorithm, instead of taking this exact error, we can substitute it by the a posteriori error estimator. So let's go to the numerical experiments. We are considering the leaf-driven cavity problem. We have velocity equal to horizontal velocity equal to 1 in the top boundary, and velocity equal to 0 on the left side and bottom boundaries. The Reynolds range is a moderate Reynolds range between 1000 and 5100. We have a regular mesh, and we perform a non-classical Taylor finite element, but a P2 finite element. This is a non-stable pair of finite element, but since we are considering the stabilization term on the pressure, we can assure that for this finite element pair, the insufficient stability constant is fulfilled. Okay, so we are in a good set. This is the comparison of the a posteriori error estimator evolution when we consider the inner pressure supremizer in the velocity space and when we not consider the this is when we not consider the inner pressure supremizer in the velocity space, and this when we consider the inner pressure supremizer in the velocity space. As you can see, basically, we need the same number of bases, just we are adding here one more basis because the tolerance here for the greedy algorithm is fulfilled with 16 bases, and here in 16 is a little bit greater, so but basically are the same behavior. As you can see, the tau is lower than 1 when we reach 11 bases, okay, here for 11 bases. And you can see how the tau and the posteriori estimator behaves more or less the same. Of course, it's not the same, but more or less the behavior is the same. But just is a 2 or 3 order of magnitudes greater than the posteriori estimator. Here, at the beginning of the first steps of the greedy algorithm, since we have not defined the classical posteriori estimator, we are taking the linearization that I explained you before. Okay, in those parts, in those iterations of the greedy algorithm, we are taking the linearization of the posteriori error estimator. Here I showed you the efficiency of the posteriori error estimator, just comparing the a posteriori error estimator, that is the blue line, and the exact error, okay, at the last stage of the greedy algorithm. As you can see, for both cases, more or less is 1 order of magnitude the efficiency of the a posteriori error estimator. So basically, the behavior of the exact error and the a posteriori error estimator is practically the same, but just 1 order of magnitude with respect of the exact error. But the main thing is that, okay, when we consider the inner pressure supremizer, we are increasing the dimensionality of the reduced basis space, because the dimension of the velocity space is the dimension of the velocity snapshot plus the inner pressure supremizer, while if we not consider the inner pressure supremizer, the dimension of the reduced basis space is lower. So which is better in order to choose one strategy or the other? So we have compared for both velocity and pressure, which is the error, the exact error in each iteration of the greedy algorithm when we consider the inner pressure supremizer or not. And as you can see, in both cases, the behavior of the decayment of the error for both velocity and pressure are practically the same. There is not so great difference between taking the inner pressure supremizer or not in our velocity space. So as conclusion, we can say that since the dimension of the reduced basis space when we not take the inner pressure supremizer is lower, we should choose this strategy that not considers the inner pressure supremizer because it's faster to solve it. In fact, here I showed you a comparison between the speed up when we consider the inner pressure supremizer or not. In this first table, we have that the speed up when we not consider The inner pressure supremizer, of course, depends on the Reynolds number, but it's about 3, 4, 7,000. Okay, and when we consider supremizer, since the linear system is a little bit bigger, it takes a little bit more time in order to get the solution. I think this number is wrong. Yes, because it should be the same number. But of course, the online time in order to solve the linear system, of course, is a little bit greater here than here. And as you can see, for both the error are more or less equivalent. There is not such much difference in both cases. So let's go to the second part of the talk, in which we are changing our mind, not taking mathematical, let's say, theories in order to build the posteriori estimator, but take advantage of some physical properties of the solution that we suppose. This is a work in collaboration with Alejandro Bandera, Cristina Caravaca, Tomás Chacón, and Macarena Gomez. And this work is recently published in this paper. Okay, and the idea is, since the classical Bresci-Rabiat theory, a posteriori estimator, is very difficult to compute some constant, of course, the beta constant and the rho constant for an steady problem, we need to, let's say, change our mind and think to another possibilities. Moreover, in this classical, let's say, Bresci-Rabiat theory, we have some restrictively mathematical hypotheses that not always is satisfied. So we consider some physics properties of the solution. So we know that the Kolmogorov cascade is satisfied when we take some turbulence models, and we know that the energy spectrum, the turbulence energy spectrum in the inertial range follows this law, where here epsilon is the viscosity dissipation. Okay, we know that the energy spectrum should follow this law in the inertial range. So since we are taking the Smagorinsky model for this case, that is a turbulence model that solves a part of the inertial spectrum, we can say we can think that our solution in a part of the inertial spectrum will follow this law. So let me recall the Smagorinsky model, but now we are adding the time derivative in order to get the anesthetic Smagorinsky model. We are in a new, let's say, framework. We consider a simpler problem, let's say, because we consider a periodic flow, okay, over on the square also. And we will suppose that the initial condition of our problem is well developed. So we can see that the energy spectrum follows this k to the power minus 5/3 law of Kolmogorov. Now, in this problem, we are leading with a higher Reynolds parameter set. We are considering Reynolds between 1,000 and 60,000, okay? Since this was a different problem, we deal easily with P2, P1 Taylor-Hurd finite elements, so we are not adding stability term for the pressure. We are dealing with a stable pair of finite elements. And we consider a semi-implicit scheme for the time discretization. Okay, this is the numerical setting of our problem. As I said you before, we consider that the initial condition is well developed. So for that, we need that the velocity, we consider the velocity, the initial condition by this way, where here v is such that its Fourier transform is given by this quantity. So we are assuring that we are considering that we are solving properly the initial a part of the initial spectrum. In fact, if we compute it for wave numbers about 5 and 32, we can practically solve. We can see how the initial spectrum is well computed. This is the initial solution, the initial condition of our problem, and this is energy spectrum. Okay, so in the reduced basis framework, how we proceed. In this case, we are not taking only a greedy algorithm, okay, but also a POD procedure in order to reduce the time, let's say, parameter. So we consider POD for time and greedy for the physical parameter. And we can choose different POD greedy approaches in the sense that it depends how we construct or reduce basis space. We can deal in a first way a complete POD, that is, okay, we compute the time snapshots for each parameter value, and we perform a POD over all the snapshot of the time snapshot for every selected parameter value. Okay, so this is the procedure that takes more information about the physical solutions. We can also consider another kind of POD that we call it hierarchical POD, that it's, okay, we select a parameter value and we perform a POD. And we add it to the previous reduced spaces. That is, when we select a new parameter value, we compute all the time snapshots and we perform a POD. And we just add this POD space, this reduced space, to the previous one. Thanks to that, this velocity and pressure space are hierarchical, just the classical, let's say, greedy space or reduced basis space that we construct in the previous case when we consider only the Reynolds number as a parameter. Moreover, we can consider the incremental HI POD that is a little different. In this is practically the same that the hierarchical POD, but we perform another POD to this velocity, to the enhanced velocity and pressure space. So it's the same of before, but just performing a second POD in order to reduce the dimensionality of this reduced basis space. And finally, that the last strategy that we can follow is that the one that we have called the reduced POD. That is adding to the previous space the new snapshot in time and perform a POD over this space. So we have the previous space, we add the time snapshot for the new parameter value, and we perform a POD. Okay, those are the 4 strategies that we can follow. In order to see what is the best one, in order to validate or later on or a posteriori error estimator, we compare it, but using the exact error. If we compare it, we can see that although at the first stage of the greedy algorithm, the reduced POD behaves better because the error is lower, the problem is that at some point it stagnates and it doesn't reduce the error between the finite element solution and the reduced basis solution. You can see how the hierarchical POD and incremental H POD have practically the same behavior, a little bit better than the hierarchical POD. And of course, the better one is the complete POD because it has the most information of all the parameter and time snapshots. Here is just the same errors, but measured in different norms. This is the L2 norm, and this is the L infinity norm. But we are measure the exact error. Okay, there is not such much difference. So from now, we are considering the complete POD in order to validate our a posteriori error estimator. So, in which consists our idea of the new Kolmogorov a posteriori error estimator? Okay, we can suppose that if we solve it properly, the high fidelity solution should verify that its energy spectrum should follow this law, this k to the power minus 5/3 law. So we just adjust the slope of the function depending on the Reynolds number. This alpha will depend on the Reynolds number, but the slope of the function should be this k to the power minus 5/3. So the idea is to define the indicator just the one that we solve for the reduced basis solution and the theoretical one, the theoretical finite element one. And of course, we have to minimize this alpha in order to get the proper slope, let's say, okay? Here, this K1 and K2 is the weight numbers in which we solve the inertial spectrum, okay? So now the idea is not taking a posteriori estimator based on the residual pass, but based on the energy spectrum. On the reduced basis algorithm, we perform practically the same as before. In a first step, we we select a parameter value, okay, on the parameter range, and we compute all the time snapshots, some time snapshots for velocity and pressure. We consider a POD greedy algorithm strategy, as I explained you before. As I say, we choose the complete POD, and we compute the a posteriori error estimator for each parameter value. And we will select the new parameter value according to this a posteriori error estimator. What's the difference between the previous a posteriori error estimator and this one a posteriori error estimator? Here we can see it graphically. Okay, this is the energy spectrum. This continuous blue line is the energy spectrum of the finite element solution. In the previous posteriori error estimator, the posteriori estimator converts to 0 because is based on the residual, and the residual tends to 0 when we increase the dimensionality of the reduced basis space. But now, the a posteriori estimator of the reduced basis solution doesn't convert to 0, but it converts to the finite element energy spectrum. So the a posteriori estimator now doesn't tend to 0. So if we select as a criteria just taking the maximum of the a posteriori estimator, it may happen, and in this case happens, that we will reselect again the same parameter value. If you follow here the graph, this is the reduced basis energy spectrum for the first greedy algorithm. If we choose, okay, the greater one is not a problem, and we perform another greedy iteration, and we get this yellow line a posteriori error estimator that is given by this quantity. Okay, now the a posteriori error estimator for the higher value of the Reynolds number is the finite element one. If we select another one, okay, there is not a problem. We select this parameter value because this is higher than this, and we get this purple line. What happened now? In this purple line, the maximum of the a posteriori error estimator is again the maximum value of the parameter. But of course, the error maybe is not committed here, but is committed in some sense here because is farther than, in fact, is over here, but is farther from the finite element energy spectrum. So the strategy that we will follow is that, okay, at the first steps of the greedy algorithm, we will choose, of course, the maximum of the a posteriori error estimator in order to follow, let's say, the same strategy as before. But when we get that taking the maximum, we reselect the parameter value, we will compare the new posteriori error estimator with the previous one. And since the posteriori error estimator for the reduced basis solution or the energy spectrum for the reduced basis solution converts to the energy spectrum of the high fidelity problem, we can say that in the last steps of the greedy algorithm is a good strategy to look the maximum difference between the previous a posteriori estimator and the new a posteriori error estimator. And this give us the new parameter alpha, because we are supposing that the new a posteriori error estimator is practically the finite element energy spectrum. Here I compare you in this table the maximum of the a posteriori error estimator, and here the difference. So the difference of both a posteriori estimator, and here the maximum over mu of the exact error. Okay, this is a comparison between taking the a posteriori error estimator for selecting the parameter value, okay, or taking the exact error for selecting the new parameter value. As you can see, we are not plotting here the number of the Reynolds number, but are practically the same. The number of bases are practically the same in the reduced order level. So also the error, the exact error is the decayment is practically the same. Here I show you some comparison between the finite element solution for velocity and the reduced basis solution of the velocity. Here I show you the error that is basically 10 to the power minus 7. okay, at the final time step. And finally, in order to validate that, okay, we are considering a good way in order to choose the parameter value, we compare choosing the parameter values by the a posteriori estimator, or just taking a equispaced sampling of the parameter value. Random, okay, we choose an equispaced sampling of parameter value. Here is the evolution of the exact error into different norm, in the L infinity and L2 norm, okay? And maybe easily we can see here how the error, even in the L infinity, the error of between the high fidelity solution, the exact error of the high fidelity solution and the reduced basis solution, when we choose the equispaced sampling in order to choose the parameter value, is higher than if we consider the a posteriori error indicator in order to choose the parameter values. Even more, practically, the behavior of the solution is the same if we take the a posteriori error estimator or the exact error. So, in some sense, we can say that choosing the cheap posteriori error estimator is practically the same that taking the exact error between the high fidelity solution and the reduced basis solution. So as conclusion, we have developed two different kinds of a posteriori estimator, one based on a classical mathematical residual path Rabiar theory, and another one based on physical properties. And as future work, we maybe want to deal also with new a posteriori estimator for stabilization, for reduced basis model with stabilization not only on the pressure but also in the convective term. Of course, this Kolmogorov a posteriori error estimator, we will use it for the wind turbines problem in the area project that we are involved. Also, we can consider wall laws in order to get a proper full order solution, a good full order solution. And finally, think about other kinds of posteriori error estimator based on physical properties of the solution. Here are some complementary bibliography and nothing more. Thank you for your attention.
Thank you so much, Enrique, for this nice talk. It was really interesting. And for now, I would like to open the questions session. And from the audience, if you have comments or question, please unmute yourself and join us. Yes, Treyan.
I was asking questions. Oh, so first of all, I mean, Enrique, this was an excellent talk. Thank you. I really enjoyed it. So I need to think a little bit more about this. But so basically, let me try. I have a question, but yeah. Before I ask the question, let me try to summarize if I understand correctly. So you have two types of a posteriori estimators to choose your to construct your reduced basis, right?
Yes. Yes.
One is based on the Rabiar Rabiar theory, and the other one is based on physical type of insight, the Kolmogorov statistical theory of turbulence, right?
Yeah.
And if I understood correctly, so at some point, I don't know the slide, the slide you did that, but you basically said that for the physical error estimators, you looked at more complicated problems, so time-dependent problems, not more complicated, but time-dependent. No.
For time-dependent problem, the classical one is harder to compute.
Yes, exactly. So you said, because of this, I'm looking at these physical type of error estimators. And so is it correct to understand so is it correct to state that the physical one is probably more practical in if you had like turbulent flows like the wind turbines, then probably that would be the one to so that's very good. I agree completely with this. My question is, when you compute these error estimators for the physical one, so are the a posteriori error estimators, are they expensive? Do you have to compute the spectrum? How does it go? So the computational cost, how is that?
It's not so much expensive because we deal with the Fourier transform. I forgot it. Maybe I'm not explained better. Maybe for the following talks, I will explain better how we construct the energy spectrum. And we use the fast Fourier transform in order to compute the energy spectrum.
I see. So this
So thanks to that, we can perform the posteriori error indicator online, let's say.
I see. It's fast. Okay. Yeah. All right. That's very good. I mean, so I'm a fan of the second one,
not,
the physical. Yeah. Right.
Okay. We don't have anything because we can compute the exact error. It's faster than, of course, of the exact error. If not, we have nothing.
Yes. Fair enough. Okay, great. Thank you. I really like the presentation. I think it's a very good idea. Thank you.
Thank you, Traian.
Further questions or comments?
I can ask a curiosity.
Yes.
So at the beginning of this second part, Enrique, you said that you had to have an assumption on the initial condition.
Yeah.
So what if that assumption doesn't hold? So how can one still get something out of this? And is it in practice that assumption hold or not?
In practice, we have assured that the inertial energy spectrum should follow this law. So the flow should be well developed. If not, we are not considering anything. Okay. Of course, this has a problem with the walls. So we have to compute maybe not the energy spectrum over all the domain, but only on a part of the domain where we know that the flow is well developed. Okay, this is the idea we have for the wind turbines. Not taking the whole domain, because near the walls this shouldn't be verified, as you can see also for periodic flow at the beginning and at the end. This is not verified. We only have this energy spectrum in the correct way in a certain wave numbers, for a certain wave numbers. We have to prove if we have a developed flow only on a part of the domain. This a posteriori estimator is still valid, but of course we have to prove it.
Okay, thank you.
Sorry, Tran, please go ahead.
I think that Valentin maybe wants to ask a question, so I'll ask, maybe he can ask the question and I can come back.
Thank you. Thank you for the great talk. Very interesting. I have a question about two-dimensional and three-dimensional. So maybe I miss it, but okay, I have two questions. Like first, it was I thought you were working only in 2D. So how it go to 3D, and also the spectrum here is -5/3, which is a 3D spectrum, like for 3D turbulence, I think. So
we expect that, yes. We are starting now with 3D problems. Okay, we are for both posteriori estimators. We are starting with 3D problem. In fact, the wind turbines problem is a 3D. We expect that the spectrum follow this law. We expect it, and if not, we can expect to think about another physical property that we could take. But yes, for 3D problems, of course, there are more difficulties, and of course, we are thinking on it. Is the step we are taking now? Go to the 3D problems, realistic 3D problems. In fact.
Okay, thank you. And for 2D, do you use a -3 slope, or you use also -5/3?
-5/3.
Okay. Thank you.
And Jan, do you want to ask further, or?
Yes. Yes. So I first of all, I think that Valentin's question was very good, and I think that maybe this is more like a proof of concept, like a two-dimensional type of numerical illustration. But as Enrique said, and Valentin implied, you need to go to 3D to see, to see this Kolmogorov energy spectrum in real type of application. So yeah. So my question is about the first part of the talk. So did I understand correctly that for the first Enrique, for the first a posteriori error estimator, so basically you considered without supramisors, but with at the ROM level, but with pressure stabilization, and then you also
yes, both are with pressure stabilization.
Right. So my question is this: do you need supramisors? Because if you have pressure stabilization, my understanding is at the ROM level. That's what I'm interested in. Then my understanding is that you do not necessarily need the supramisor, because as you said, that would enlarge the size of the problem.
Yeah.
Is that fair to say?
Yeah.
Okay.
You don't need it.
Okay. Very good. Okay. Thank you. I appreciate it. So I think we're on the same page here. Thanks.
Okay, I think today we have all, and thank you so much again, Enrique, for this nice talk, and see you next week. Bye-bye.
See you.
Thank you. Excellent talk.
Thank you.
See you.